All right, this function is written in the form f of x equals a over x minus h plus k. In order to find your vertical asymptotes, those are the zeros of the denominator, anything that makes the denominator 0. So x equals negative 2 is a vertical asymptote. For the ones that are in this form, the asymptotes are really helpful to give us a framework for the graphing. The horizontal asymptote is whatever your vertical shift is, because usually it's the x-axis, so if you shift up, then whatever your vertical shift is. So your horizontal asymptote is y equals 1. Positive functions open to the branches open toward the first and third quadrants. This one is a negative, so it's going to open toward the second and fourth quadrants. But we still have some more things to find. Wholes would be anything that reduces to 1, whatever makes that equal to 0. Nothing's reducing here, okay, so there's not going to be any wholes in any of the ones that are in this form. All right, x-intercepts is whatever makes y equal to 0, okay? Whatever I plug in for x and you get out 0 is your x-intercept. So we're going to solve a simple equation. Instead of f of x, I'm going to say 0 equals negative 3 over x plus 2 plus 1. I just decided to put that negative on the 3. So subtract 1 on both sides. Negative 1 is equal to negative 3 over x plus 2. And then multiply both sides by x plus 2. On the left side, I'm going to end up having negative x minus 2 equals negative 3. Negative x equals negative 1, x equals 1. So that's my x-intercept, 1 comma 0. I'm going to put a dot there, and yay, that gives me less work to do. You're supposed to plug in 2 values to the left of the vertical asymptote and 2 values to the right in order to graph it, okay? 2 to the left, 2 to the right. This means 1 less value for us to plug in because we have a point to the right of the vertical asymptote. And then our domain is x is a member of the set of all real numbers, but x cannot equal any wholes or vertical asymptotes. We don't have any wholes, so it's just the vertical asymptote that x can't be. And they don't ask for a range. So let's plug in 2 other values. I am going to do this on my own to expedite this process, but I'm going to choose negative 3 and negative 4 because they're directly to the left. And then to the right, I'm going to choose 0. I could also choose negative 1, but 0 is going to give me enough of a picture and it's easier. All right, negative 4 to 2.5, negative 3 up 4, 0 down 2.5. And here are my branches. Make sure they're not crossing those asymptotes. Slightly different form, okay? It's not exactly like crazy like this one, but sometimes the simpler ones can get us. So let's factor the denominator to see if anything reduces, which we know it's not because it's just a 4, and 4 was not the GCF here. So we have vertical asymptotes. Whatever makes the denominator equal to 0. So zeros of the denominator after you've figured out wholes. So no wholes, let's just say none. That should definitely be the first thing you look for actually is wholes. So vertical asymptote is whatever makes this denominator equal to 0. It looks like there are 2 of them. So x equals 0, right? Taking care of this, what would make this 0? 0. And then 3 minus 3 would be 0. So I have 2 vertical asymptotes. Okay, so now let's graph them. Horizontal asymptote. The degree of the numerator is x to the 0, so 0. The degree of the denominator is 2. If the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is y equals 0. All right. Guess what that means? If you have an asymptote on the x-axis, you don't have any x-intercepts. Interesting. And my domain, as always, is all real numbers. I might as well just get it done now. But x cannot be wholes or vertical asymptotes. So 0 or 3. This means I have to plug in quite a few points, okay, right? I need to plug in 2 points to the left, 2 points in between, 2 points to the right. So here's going to be my table. I'm going to show you the points that I choose, but then pause to plug them in. So -2, -1, 1, 2, 4, 5. All right, -2, down 1/2, -1, down 1. Here's my first branch. Now, because you have 2 vertical asymptotes, this is going to look slightly different than you may be used to. So that's why I wanted to do this problem. So in between, we have 1 goes up 2, and then 2 goes up 2. That is a little weird that they're right next to each other. I decided to plug in the point in between them just to see where it goes, like what's happening there. So I actually plugged in 1.5, and you get out you get out 16/9, which is similar to like 1.7. So in between, it's actually just going down a little bit, kind of like a itty bitty baby parabola. Okay, so it's gonna go this way. It's not a parabola, okay, but it's kind of like it. Now, if this was above, this one should be below. It kind of switches adjacent. So 4, -1, 5, -2/3. Yeah, so then you know, okay, this makes sense. This is what it's supposed to look like. You can also have one that has 2 vertical asymptotes that has a branch down, a branch up, and then the one in the middle looks like more like a cubic. This one looks like a parabola, but the one in the middle would look like a cubic. And in that case, if it's in between the 2 vertical asymptotes, it's okay to cross the horizontal asymptote in between the 2 vertical. But that's the only time you can ever cross an asymptote. And let's do number 16 to finish. All right, let's factor. Both the numerator and the denominator have a GCF, and they factor further, so go ahead and do that. 3x goes into the top. And then continue. -4 plus 3 would give me that -1. And then here, take out an x, and you get x squared minus 16, which we know is difference of perfect squares. I'm going to move this whole fraction over to the most factored version. X minus 4, x plus 3 is over x times x plus 4, x minus 4. Okay, now it looks like we've got some things that reduce. So we got some holes. This reduces, so you have a hole at x minus 4 equals 0. So you have a hole at x equals 4. Oh, x over x is 1. So you have a hole at 0. You have a hole at x equals 0, which is, yeah, literally 0. Okay. So you have, whoa, 2 holes. Plural. All right. Vertical asymptotes, anything else that's making the denominator equal 0. So this one right here, so x equals -4. Oops. And then horizontal asymptote. All right, the degree of the numerator and the denominator is the same, so the leading coefficients, 3/1. That's my horizontal asymptote. Y equals 3. X-intercepts are anything that make the numerator equal to 0, of course, after the wholes. So the only thing left is x plus 3, so -3, 0 is my x-intercept. -3, 0. That's where I'm going to put a point. That makes my life just slightly easier for later. Domain, x is a member of the set of all real numbers, but x cannot be any wholes or vertical asymptotes. So that is 3 things. 0, -4, 0, and 4. So plus or minus 4 and 0. There. Running out of room here. Okay, so I'm going to plug in 0 because it's easy. And then, of course, -5 and -6. You can't plug in 0. It's undefined. Man, I just always want to plug in 0. So I'm going to plug in -1 instead. All right, -1, 2. So, and then -6 goes up to 9/2. -5 goes up 6. Now, the wholes are a little tricky. Okay, so what I would do is graph with a pencil how you know the graph looks. Even that isn't super pretty, right? Because you want to make it super neat. Okay. But then you know that you actually have a hole. You actually have a hole at x equals 0, so wherever it's crossing the y-axis. And then you also have a hole at 4, so whatever's happening at 4. So I should have a hole around here and a hole around 4. I'm going to finish this off with pen. So you have your holes and the rest of your branches.